Hello students, welcome to lecture series of Mathematics 2. I am Hitesh Manglani, Assistant Professor at LJ Institute of Engineering and Technology. So today we will discuss topic that is work done, circulation, path independence of line integral and fundamental theorem of line integrals of chapter vector calculus. So let's start. So first of all we will discuss about work done. So what is called work done? So if vector field F is force acting on particle moving along arc AB of the curve C, then line integral f dot dr integration from A to B represents work done in displacing the particle from point A to point B. So this represents work done. This represents work done, okay, in this particle from point A to point B. So we can say that work done is basically a line integral. Now we will discuss about circulation. If vector field F is the velocity of a fluid particle and C is closed curve then line integral f dot dr over a closed curve C represents circulation of F around the closed curve C, okay, of F over a closed curve C. So if F is velocity of fluid particle, then line integral over a closed curve C f dot dr will represent circulation of F around the closed curve C. Now let us discuss examples related to this. First example, find the work done by the force F, that is 3x square minus 3x I cap plus 3z j cap plus k cap along the straight line Ti plus Tj plus Tk, and where T varies from 0 to 1. So here in this example we will have to find out the work done. It is basically a line integral, so this is given by f dot dr over a curve C. So this will be integration over curve C f1 dx plus f2 dy plus f3 dz. So here f1 is ith component of vector f, so it will be 3x square minus 3x dx, okay, plus f2 is jth component of vector f, so it will be 3z dy, and f3 is kth component of vector f, so here it is 1, so it will be plus 1 into dz. Now here in this example r is Ti plus Tj plus Tk. So we will compare this r with xi plus yj plus zk, okay. So x will be t, y will be t, and z will be t. So here dx will be dt, dy will be dt, and dz will be dt, okay, and limit of t will be from 0 to 1 as it is given in the question, okay. Therefore work done will be integration from 0 to 1, okay. Then instead of x we will write down t because x is equal to t, so 3t square minus 3t dx, instead of dx we will write down dt, okay, plus next term is 3z and here z is t, so it will be 3t and dy, instead of dy we will write down dt, okay, plus here it is dz, instead of dz we will write down dt, okay. Now we will simplify this. So this will be equal to integration from 0 to 1 3t square minus 3t, okay, plus 3t plus 1 into dt. So 3t cancel out, so integration from 0 to 1 3t square plus of t square with respect to t will be t cube by 3, and integration of 1 with respect to t will be t. So this will be 3 into t cube divided by 3, and limit will be from 0 to 1, and here integration of 1 dt will be t, and limit will be from 0 to 1. So here first of all we will replace t by 1, then minus we will replace t by 0. So here 3 cancel out, so here 1 minus 0, so here it will be 1, plus here again 1 minus 0, so here it will be 1, so 1 plus 1 will be 2, therefore work done will be 2. Now we will discuss new topic, that is path independence of line integral. So first of all, what is the meaning of path independence of line integral? So if vector field f is conservative, then line integral along the curve C from points A to B is given by integration f dot d, that is equal to phi b minus phi a. So here line integral depends on the start value and end value, so it is independent of path. So here line integral depends only on start value and end values, so it is independent of path. Hence for conservative vector field, line integral will be independent of path. So here if f is conservative, then line integral will be independent of path. So we can say that for conservative vector fields, line integral will be independent of path. Now we will discuss fundamental theorem of line integrals. So if f is vector field which is given by f1i plus f2j plus f3k, then there exists a differential function phi such that f is equal to grade phi, that means gradient of phi, so which is given by I del phi by del x plus j del phi by del y plus k del phi by del z. If and only if line integration from a to b f dot dr is independent of the path joining a to b. So this is called fundamental theorem of line integrals. If f is vector field given by f1i plus f2j plus f3k, then there exists a differential function phi such that f is equal to gradient phi, and gradient phi is defined by I del phi by del x plus j del phi by del y plus k del phi by del z. If and only if integration from point A to point B f dot dr is independent of the path joining A to B. So this is called fundamental theorem of line integrals. So this line integral will be independent of the path if f is equal to gradient of phi. Now let us discuss example related to this. First example, if f is equal to 2xy plus z cube I cap plus x square j cap plus 3xz square k cap, then show that line integral f dot dr is independent of path of integration, and hence find the integral where c is any path joining point 1, -2, 1 and 3, 1, 4. So here we will have to show that line integral is independent of path of integration. So to prove this, we will have to show that curl of f is equal to 0 vector, because as we have discussed earlier in path independence of line integral, if f is conservative vector field, then line integral will be independent of path. So meaning of conservative vector field is curl of f should be 0 vector. Okay, so here first of all we will find out curl of f, so which is given by determinant of I, j, k, del by del x, del by del y, del by del z, and here ith component of vector f is 2xy plus z cube, then jth component of vector f is x square. Okay, then kth component of vector f is 3xz square. Okay, now we will take determinant of this, so it will be I cap in bracket del by del y of 3xz square, okay, minus del by del z of x square. Okay, then minus j cap del by del x of 3xz square minus del by del z of 2xy plus z cube plus k cap in bracket del by del x of x square minus del by del y of 2xy plus z cube. Okay, if we take partial differentiation of this function with respect to y, then x and z will be constant, therefore derivative of this function will be 0. Same way here, if we take partial differentiation of x square with respect to z, then it will be 0 because here x will be a constant. Now if we take partial differentiation of function 3xz square with respect to x, then it will be 3z square because derivative of x with respect to x is 1 and z and 3 are constants. So it will be 3z square. Same way, if we take partial differentiation of function 2xy plus z cube with respect to z, then x and y are constant, therefore derivative of this term will be 0 and derivative of z cube will be 3z square. Okay. Now if we take partial differentiation of function x square with respect to x, then it will be 2x, and partial differentiation of function 2xy plus z cube with respect to y will be 2x because derivative of y with respect to y is 1 and derivative of z cube will be 0 because z is a constant. So this will be curl of f, that is equal to I cap in bracket 0 minus j cap 3z square minus 3z square plus k 2x minus 2x. So this will be equal to 0i plus 0j plus 0k. Therefore curl of f is equal to 0 vector. Therefore we can say that integration f dot dr over a curve C is independent of path of integration. Clear? Because as we have discussed earlier, if curl of f is equal to 0 vector, then line integral will be independent of path of integration. Now we will have to evaluate this integration where C is any path joining 1, -2, 1 and 3, 1, 4. So for that purpose we will have to find out scalar potential phi, because integration f dot dr will be from point A to point B, so it will be phi b minus phi a. So first of all we will have to find out scalar potential phi. Okay. So here to find scalar potential scalar potential function phi, we know that f is equal to gradient of phi, and gradient of phi is defined by I del phi by del y plus k del phi by del z. Now we will compare ith component of f with this. So here ith component is del phi by del x, and here ith component is 2xy plus z cube. Therefore del phi by del x will be 2xy plus z cube. Same way we will compare jth component. Okay, so here jth component is del phi by del y, and here jth component is x square. Therefore del phi by del y will be x square. Same way we will compare kth component. So here kth component is del phi by del z, and here kth component is 3xz square. So del phi by del z will be 3xz square. Therefore here del phi by del x will be 2xy plus z cube, and suppose this is equation number 1. Now integrating equation 1, integrating equation with respect to x. So if we take integration of equation 1 with respect to x, then integration of del phi by del x will be phi, and here 2y will be as it is, and integration of x with respect to x will be x square by 2 plus z cube will be as it is, and integration of 1 dx will be x plus constant, that means some function of y and z. Okay, so if we simplify this, so 2 cancel out, so this will be x square y plus xz cube. So here del phi by del y is x square. So suppose this is equation number 2. Now integrating equation number 2 with respect to y. So integration of del phi by del y will be phi, and integration of x square will be x square y, because here x square will be constant and integration of 1 dy will be y plus constant, that is some function of x and z, because x and z are constants. Okay, now here del phi by del z that is equal to 3xz square, and suppose this is equation number 3. Now integrating equation 3 with respect to z. So integration of del phi by del z with respect to z will be phi, and here integration of 3xz square with respect to z will be 3x into z cube by 3, because here 3x will be constant, and integration of z square with respect to z will be z cube by 3 plus constant, that is some function of x and y, because x and y are constants. So if we simplify this, then 3 cancel out, so phi will be xz cube plus some function of xy. So here phi is equal to xz cube plus some function of xy. So here phi is equal to xz cube plus some function of xy, and here phi is equal to x square y plus some function of xz, and here phi is equal to x square y plus xz cube and plus some function of yz. So overall phi will be, so if we write down overall phi, so therefore overall scalar potential phi will be x square y plus xz cube plus constant c. So how to write down overall scalar potential phi? We have to collect all the terms of phi. Okay, so if there is any common term, then we have to write down only one time. Now as we have to find out the line integral f dot dr, so that is equal to phi b minus phi a. So here a is initial point, that is 1 minus 2 1, and b is final point, that is 3 1 4. So first of all here we will put x equal to 3, y equal to 1 and z is equal to 4 in this. Then minus we will put x equal to 1, y equal to minus 2 and z is equal to 1 in this scalar potential. So this will be x square y, so 3 square, so it will be 9, y is 1, so 9 into 1, okay, plus xz cube, so here x is 3 and z cube, that is 4 cube, so it will be 64, so 3 into 64, okay, plus c, so this is 5b minus 5a. Now in scalar potential, first term is x square y, so now here x square, so 1 square will be 1 into y is minus 2, so it will be minus 2, okay, plus second term is xz cube, so x is 1 and z is also 1, so 1 cube will be 1 plus c. So if we simplify this, so here 9 into 1 9 plus 64 into 3 will be 192, okay. Then here minus 2 and minus, so plus 2 minus 1 and c cancel out, so it will be 202. Therefore value of line integral is 202. So this is how we can evaluate the line integral when line integral is independent of path of integration. So in this lecture we have discussed about work done, circulation, then path independence of line integrals, then fundamental theorem of line integrals. Thank you for watching this lecture. I will see you in the next lecture.